At 603 kilometers per hour, something happens that shouldn't be possible on land. A train moves so fast it seems to detach from the world beneath it. Then the wheels retract. And suddenly the train stops touching the ground. It begins to float. This is not science fiction. This is not a prototype dream. Japan has been chasing this moment for 60 years, and most people have never even heard of it. Because to build it, they aren't just creating a railway, they are carving a 286-kilometer bypass through the very spine of a nation. 86% of this route doesn't exist on the surface. It disappears into solid mountain because there was no alternative path left. What began as a $9 billion vision has now grown into a $72 billion engineering war against geology, pressure time, and physics itself. To complete it, engineers must drill through 246 kilometers of mountain, survive collapsing rock formations, underground rivers, and conditions deep. Underground colder than the surface of Pluto. This is the Chuo Shinkansen, the fastest train ever built. And this is the story of how Japan is building a train that flies through a mountain, and why it almost never happened. The year was 1964. Japan launched the Shinkansen, the world's first bullet train. It changed everything. But today, the original Tokaido line is at a breaking point, launching 12 trains every hour. There is no more capacity. Japan needed a bypass, but the coastal route was already occupied. The Maglev is the answer, cutting straight through the peaks. Research began in 1962. It took 63 years to turn those raw equations into a functional railway. In 1977, the first 7-kilometer test track in Miyazaki provided the first proof. Levitation worked. Superconducting magnets held the weight. The next step was the Alps. In 1990, geological surveys began in the Southern Alps. Engineers spent 19 years studying the rock before a single tunnel was even approved. The geology here is 300 million years old, and unlike anything humans have ever tunneled through, we are talking about 14 meters of overburden. The weight of the mountain itself pressing down. Fault zones and underground rivers with rock pressure so intense it can crush steel. In 2011, after 49 years of research, construction finally began. The Yamanashi test track came first. 18 kilometers of real maglev railway built to prove the impossible. They used the new Austrian tunneling method: drill, blast, shotcrete, and rock bolt. It was a grueling 6-hour cycle repeated every single day. They drilled pilot tunnels first, sampling the rock before the main machine committed to the face. The precision required is staggering. The guideway must be accurate to millimeters over kilometers, laser-checked at every section. This isn't a normal railway. The motor isn't in the train, it's embedded in the track walls. 18 kilometers of electric motor built into the concrete with figure-8 coils that handle levitation, guidance, and propulsion all in one. Every coil is powered, every sensor connected, and every millimeter of the train's position is monitored simultaneously by a dedicated control center. When the first test train arrived in 1995, it looked like a capsule from another world. No wheels were visible, no overhead wires for power. In 1997, the tires retracted for the first time and the train rose 10 centimeters, floating on invisible force. By December of that year, it hit 531 kilometers per hour. Japan tested everything. 200,000 people rode the test train before a single commercial passenger was even considered. In 2014, ground was broken on the real line, the biggest railway project in history. In Tokyo, they are building a new station 40 meters deep, directly beneath the existing bullet train station without stopping the trains above for a single second. They used diaphragm walls, continuous concrete retaining walls, to secure the site before excavation. The tunnel boring machines, or TBMs, are too large to be lowered whole. They are assembled piece by piece in the launch shaft, 14 meters wide and weighing 4,000 tons. As the TBM advances 15 meters a day through urban ground, people in the shops and homes above feel absolutely nothing. But as the urban soil turns into alpine rock, the machines begin to fail. The tungsten carbide disc cutters on the face wear down every 50 meters. Replacing them is one of the most dangerous jobs in construction, requiring workers to enter a pressurized chamber at the tunnel face. When the 300-million-year-old schist rock proved too unpredictable for the models, an emergency redesign was called. The TBMs were replaced by the slower, costlier NATM method in the worst sections, leading to a 5-year delay. The mountain fought back at every turn. High-pressure underground rivers were encountered at depth, requiring them to be grouted shut or drained away. 10,000 liters of water are pumped out of the Southern Alps tunnel every single minute. Even the excavated rock is reused, crushed on site to be used as concrete aggregate for the tunnel lining. To manage the scale, 60 separate construction contracts are running simultaneously across 60 different sites. The stations are equally ambitious. The Kofu Cavern is an underground station carved from solid rock, larger than most surface stations, with no columns supporting the roof. Instead, rock anchors drilled 20 meters into the mountain do the heavy lifting. Once the tunnels are complete, the hardest part begins, installing the guideway. With a tolerance of just 1 millimeter over 50 meters, there are 0 exceptions. 580,000 individual coils are installed by hand. The physics of the train itself are a masterclass in extremes. The nose is 15 meters long, shaped by 3 years of wind tunnel testing to prevent the violent pressure wave created when entering a tunnel at 500 kilometers per hour. The superconducting magnets inside are kept at -269 degrees Celsius, colder than the surface of Pluto, using liquid helium. Below 160 kilometers per hour, the train runs on tires. Above that speed, they retract automatically, and the train flies. Every system is monitored by 1,200 sensors per train. During testing, when a magnet quenched at 400 kilometers per hour due to track vibration, the safety systems stop the train instantly, and engineers redesign the mountings on the spot. They've even simulated earthquakes at 500 kilometers per hour. The U-shaped guideway physically prevents the train from ever leaving the track. On April 21, 2015, they pushed the limits, 603 kilometers per hour, a world record. Yet, inside the cabin, there was almost no vibration. You could read a newspaper. At these speeds, the Maglev uses only half the energy of an equivalent airplane flight per passenger. But engineering wasn't the only obstacle. A single signature from the governor of Shizuoka stopped the project for 4 years over concerns for the water supply of 600,000 people. The delay pushed the budget from $9 billion to $72 billion. It wasn't until the governor resigned in 2024 that construction could finally resume. Today, 30,000 workers are still building. They are facing labor shortages and groundwater levels that drop near the tunnels, requiring immediate modifications to the lining. The 14% of the track that is above ground uses elevated viaducts and noise barriers so effective that a train passing at 500 kilometers per hour is quieter than a busy road. China may have unveiled its own maglev, but Japan is refining its technology even as they build, introducing lighter and more efficient cars in 2025. With 60% of the tunneling now complete, the target is 2034. Everything built so far, every millimeter of precision, and every $1 billion spent is for a single goal: to make Tokyo and Nagoya 40 minutes apart. The fastest thing on land isn't just a train. It's a 60-year testament to human persistence, cutting through the heart of the mountains.